So I need to define a thing. The thing I'm going to define is going to be pretty useful. It's also something you're super used to having. So I'm going to say a set of vectors v1 through vn. Right, so I've just got some set of vectors. This is a usual thing we talk about, right? Is orthonormal, which is going to have two pieces, right? There's the ortho piece and the normal piece. If vi dotted with vj, so for some pair of vectors, right? The dot product is either 0 or 1. Quick question. Can you guys fill in the comparisons between I and j here intuitively? So I'm going to put one symbol in between each of these. Tell me give me a guess as to which symbol is going to be what.
It's only 0 if it's perpendicular.
Good. So it's going to be 0 if it's perpendicular. Is it useful for me to think about vectors that are perpendicular to themselves? What vector is perpendicular to itself?
0 vector?
Yeah, only the 0 vector, right? Okay, so I'm going to say they're perpendicular, right? Probably going to say they're perpendicular if they're not the same vector, because I'm not going to be really interested in the 0 vector here. So I'm going to say for I is not j. And when's that going to imply that I get 1?
When they're equal?
When they're equal. My overriding example for this, you guys got one?
The identity matrix?
Good, the columns of the identity matrix, which I'm going to label as the set of vectors I, j, and k, a subset of R3. So this property of being kind of unit length, you guys see unit length here? That's going to be kind of the normal part of this. So when I say orthonormal, I kind of want you to think the two words, ortho and normal. The normal part, I want you to kind of think of that as unit length. And what's the ortho part?
Orthogonal?
Yeah, orthogonal perpendicular, right? So I want you to think about these sets as sets of perpendicular vectors that are all unit length. You guys recognize why these are going to be useful for me?
Oh.
Yeah, if I could construct if I have a function space, and I can construct a set of orthonormal vectors in that function space, then those are going to act like my usual concept of a basis. And I like that concept of a basis so much that I'm going to try to make it anywhere I can. You guys with me? So these are going to be pantomimes of our usual basis sets. So I'm going to give you a new letter too. And this isn't quite a definition. This is going to be a convention. So if I use a capital Q, what I'm going to mean is I'm going to mean a matrix whose vectors are what do you mean vectors? That was dumb. What do I mean by vectors in a matrix?
Columns?
Yeah, I mean columns. So a Q is going to be a matrix with orthonormal columns.
Question?
Yes?
But this Q has to be squared.
No. Good question. So, that is absolutely an observation I need to make. They are not necessarily square. Guys with me on that? What is your go-to example of one of these, and why is that a bad idea?
Against the identity matrix.
Good. Your identity matrix is your go-to example for one of these. Why is that a bad idea?
Because it's square?
Because it's square, and also because it's special in a lot of ways.
Yeah.
Right? These matrices are going to be similarly special in some ways, but they are not going to share all properties of the identity matrix. So do not make the identity matrix your go-to version for these. You good with that? In my head, my cartoon for these are what are called the rotation matrix. So my example, like the one I have in my head, not the identity matrix, although that is a good one, are these R thetas. Have you guys seen these in the homework? Let me rephrase that. You've seen these in the homework. Do you remember having seen these in the homework?
I remember seeing them, but that's about it.
Okay. These are the two-dimensional rotation by theta matrices. So cosine theta, sine theta, and minus sine theta. I always have to be a little careful writing these down. Cosine theta. Why do I have to be a little careful writing these down? Well, it's pretty easy to fill a matrix with cosines and sines, right? And I can tell that the determinant of this matrix, cosine squared minus sine squared. Good talk. 6 years I've been teaching here. That's the first time that phone is right. All right, so I have cosine squared minus sine squared for a determinant, right? So what can you tell me about the determinant of these?
It's 1.
The determinant of my R thetas is 1. Okay, we're going to get into what that means in chapter 5. But that seems like a special thing, right? So it's relatively easy to throw this stuff in here. And the reason I always have to be careful writing these down is sometimes I accidentally write down the R minus theta matrix if I don't have my notes open. Because it's relatively easy to make a matrix that rotates the other direction. This one rotates this way. Pretty sure. Probably should triple check my notes. How could I tell? Pick a vector and multiply it, right? So I'm going to pick the I vector. You see that? So I'm just going to take R theta, and just quickly to double check myself, because I'm paranoid about these, I'm going to multiply it by 1, 0, right? Okay? So that's going to give me a new vector, right? So when I pick this up and drop it on, right, I'm going to get
Cosine and sine.
cosine theta, sine theta. So if I think about what the picture is, right, I have my I vector, right? And then I rotated it, and now I have cosine sine, right? So that's here. So that went up by theta. Okay, cool. This is the usual one. This one rotates this way. If I wanted to rotate by minus theta, how would I do that?
Would we swap the
Or
color?
it's all the same.
That's not a half bad idea. It gets a little weird. So don't just slap negative signs on the whole thing, because that's a reflection.
Swap cosines and sines.
How about plug in a minus theta into all of these?
But.
Right.
Okay, yeah, no, yeah.
So if I want to rotate by minus theta, right, I want it to go the other direction. So it's the same matrix, I just need to rotate by minus theta instead of theta. So if I plug a minus sign in, minus theta in for all of these, cosine's even, right? So those two will stay as cosines, and the sine will switch on those two.
Yeah.
You guys see
Wait,
that?
so switching the columns wouldn't do anything.
Yeah, switching the columns won't. That'll give you a reflection or something.
Okay.
You guys good with this? Okay. These are my kind of go-to. Can you tell me that these are orthonormal?
Well,
What do we need to do to check that this set of vectors, right, that my two columns are orthonormal?
Well, you take the dot product of the two columns as vectors. And
Good.
then take the dot product, or, yeah, the dot product of themselves.
So if I want to check that they're orthonormal, right, I need two things. Thing one, ortho. Thing two, norm. So to check ortho, I take my two vectors, cosine theta, sine theta, and I dot product that with the other vector minus sine theta, cosine theta. So we get minus sine cosine plus sine cosine gives me
0.
0. Okay, that's the first check. We have an ortho set at least.
And would they be normal because the max is 1?
No.
Well, what do you get by doing them, dotting them themselves?
Yep, I need to take them and dot them with themselves, right?
Oh yeah, okay. Yep. that
So
makes
if I take cosine theta, sine theta, and dot it with cosine theta, sine theta, I get,
Cosine squared theta, sine squared theta.
good, I get cosine squared plus sine squared is 1 by the, what do you call that thing?
Pythagorean.
Very nice. Should I shut up Ryan up for a little while? So, Pythagorean identity, how's the other one go?
Oh,
Because this is, so far I only checked that the first column was normal, right?
it's the same.
It's pretty possible that the first column could be normal and the second column wouldn't be.
It's the same thing because negative sine squared is.
Perfect. Yeah, same thing, Pythagorean identity again.
Yeah.
Good. Check, check. Okay, so these rotation matrices I could call Q's. I'm not going to because they're specialer than Q's, but they are my cartoon for Q's. Questions? Nothing?